That's not what you should do. Okay, so I think we have all of the content developed for applications of derivatives. I think the best way to really learn the subject well, rather than just talking about it, is to use it to solve some hard problems. So I picked a couple nice hard problems, hard in the sense that they just have several steps and they're context rich. So I've written up kind of scaffolds where we'll break these couple hard problems up into some nice manageable steps, little exercises like a scaffold, go through them, and that'll just kind of help solidify, I guess, all the stuff that we've done in this unit. And then one last thing, since I was debating about how the organization should work of later chapters, I want to actually do L'Hopital for limits at infinity in this chapter. So I think we can do that maybe 1 or 2 sessions where we do units on this. I think we can get all of the infinite limit stuff done. So that is the plan. So first, what is this first interesting problem? First, I very much like this name. I don't know how to pronounce this. I guess it's like Regiomontanus or something, but I think the guy's real name was something like Johannes Muller or something. I don't know. Mathematicians back in like whenever this was 1600s, 1700s were weird. I guess they would have like a stage name or like, like Cher or something, and they would just publish under that name. I don't know why, but anyway, so this guy's stage name was Regiomontanus. And he proposed this very interesting question, which you can motivate by saying, maybe I'm staring at a picture. So if this picture or painting is hanging from the wall, so this thing is the wall with the vertical direction being like the height. So if we know the heights of the top and bottom of the painting above the viewer's eye level, so you have a viewer who's standing on the ground, and you know these heights from the bottom and top of the picture, and you want to position the observer to maximize the angle subtended by the painting. So here are 2 examples here. If you stand way back here, then you have a certain angle theta. If you stand really close to it, you have a smaller angle alpha. So the interpretation of the angle is basically how much space in your visual field the picture takes up, right? Smaller angle means smaller real estate in your visual field, larger angle means larger. So if you want the best view of the picture where it takes up the most real estate on your eye, where should you stand? It's kind of a natural question. This question is also sometimes posed in a different way, saying this is like a soccer or rugby player. Where should the soccer player stand to shoot into the goal? If he's trying to kind of maximize this angle, which in principle should give him the best shot of getting the soccer ball into the goal. So that's another way to think about it. But okay, so this is we know we're going to have to do some maximization, but the problem's a little tricky because there's a lot going on. So the first thing I want to do is throw some letters on shit. Whenever you're given a problem statement like this, you should try to kind of make it more concrete by giving names to all of the quantities. So I'll draw this on the previous one, but let's say A is the height, the bottom of the painting, B is the top, X is the distance from the wall of the guy, the dot. So say alpha would then be the angle of elevation to the bottom, and beta is the angle of elevation to the top. So pictorially, I'll draw it for this one, the guy further away on the left rather than the guy who's closer. But if that's true, then we want the bottom guy, this distance to be A, this top thing to be B. In this case, his distance away from the painting will be X. And by angle of elevations, well, I'm going to do this thing which I like to help me remember which is which. I use the Greek letter in the same position of the alphabet for the angle which matches the letter in the Latin or Roman alphabet. So first Greek letter, first Roman letter, and B goes with beta, so this tall angle, this tall boy's beta. And those are all of the quantities in the problem, so we're in good shape. Okay, so I want to come back to this since I've now drawn it very nicely and don't want to redraw it, but the first thing, I want to do this exercise first before explaining what we're doing. So as an intermediate step in what follows, we're going to want to express the tangents of these angles, alpha and beta, in terms of A, B, and X. So let me go back here. I call this an exercise rather than a challenge because it's pretty straightforward, but I'll ask you, what should I write for tan alpha and tan beta?
Well, we see just by basic trigonometry that tan alpha is equal to A over X. I can't remember what the ones that we wanted to express this in terms of are.
In terms of A, X, and possibly B, so you don't have to use all 3, just any subset of those.
Okay.
Okay, and then beta?
And I guess tangent of beta is going to be b over x. Don't see how you could do that with an a.
Yeah, it looks good to me. So, yeah, I think this is good. So this gives us tangents of the two angles, alpha and beta, in terms of these lengths. Okay. So now let me ask you, the problem asks us to optimize the angles tended by the painting. So in terms of the letters drawn here, what is the quantity we want to maximize? What is the angle that the viewer sees?
We want to maximize the beta minus alpha.
Yeah, it looks
And
good.
in terms of this stuff here, I guess it is going to be tangent inverse of a over x minus tangent inverse of b over x.
You
But
can
I
do
don't
that.
quite as far as we want to go yet.
Yeah, that's good. So that's one way you could do it, is plug in these guys, the beta and alpha in terms of arctans, and do that. That's kind of a pain because I don't want to differentiate arctan. So we're going to use a trick, which
That's
is one that...
boring.
Wait, why is it boring?
Because who doesn't want to take the derivative of arctan?
It's actually not bad. The derivative of arctan is 1 over 1 plus x squared. It's much simpler than you would think. But I don't think we proved this. Did we?
Sarcasm intensifies. I don't know why I was being sarcastic.
Good. Okay, so you're probably asking why are you expressing things in terms of tangents? The thing we're trying to maximize over is x, right? The thing where the quantity we maximize is the angle, but the thing you can tune to get the maximum is x. So you're probably asking, why are you writing all these things in terms of x? Okay, so this goes back to the philosophy of optimization problems, because usually you go through several steps, right? You read the problem, you draw a picture and write in a bunch of letters. There's way too many letters, right? There's like 5 of them here. And in single variable calculus, we want to write one function of one variable and maybe constants that we can optimize. So we want to write a nice function of x, which expresses beta minus alpha in terms of constants. So as you say, the thing you would most naively expect would work is just putting in arctans, because then we would have a very nice expression, which is, I guess, arctan b over x minus arctan a over x, which we can optimize. That's one way to do it. Maybe we could do it after this thing. We can try it that way and check that both work. Here's the trick I would like to argue, which makes life easier for us. I claim the following. Rather than maximize this quantity, beta minus alpha, we can just maximize the tangent of beta minus alpha. You say, why would you want to do that? You want to maximize the angle, not the tangent of the angle. Well, the reason is this. Tangent is strictly increasing for this reasonable place where it doesn't blow up its argument, say 0 to pi over 2. Why is it strictly increasing? Well, we know how to check if something's increasing. You take the derivative of tangent, as you told me I think 2 times ago, is secant squared, which is 1 over cosine squared. The square of a real number is always positive, so assuming the bottom doesn't blow up, this thing's always positive. So, I mean, we know what the graph of tangent looks like. It's on a reasonable interval before we get to these asymptotes, it looks like this. So tan beta minus alpha gets bigger whenever beta minus alpha gets bigger. Well, that's very nice, though, because if we're trying to make this thing as big as possible, and this guy gets bigger whenever the thing we want to maximize gets bigger, then the maxima should occur at the same place, right? Bigger this, bigger that. So biggest this, biggest that. So instead, we can just optimize the tangent. This is a very useful trick. Often, life is easier if you want to maximize something, and you can cook up a strictly increasing function of that thing, which is easier to maximize and do that. So, anyway, I'll show you how that works. If you want, we can go back and do the arctans. But does this make sense? Are you happy with the trick?
This makes total sense.
Good. Okay. All right, so we did this. We know a over x and b over x for these guys. Now here's why this is nice. So clear back in the first tutorial, well, you did two things, right? You derived the sine and cosine angle addition formulas from Euler's identity, right? The e to the ix junk. And then you divided them and said, well, we get this nice formula for the angle addition of tangents, right? In that case, I think it was actually a plus sign between them, but it's pretty easy to just make one of them negative. I think the one you proved was tan beta that was plus tan alpha over what was it, 1 minus tan beta tan alpha or something? Something like that. But if you just swap alpha with minus alpha, then I think we would get this thing, because tangent is odd. So you can replace alpha with minus alpha, tangent of minus alpha is minus tangent of alpha, and you get this chunk over here. So this is pretty good, because now we want to maximize this. Instead we can maximize this thing, and then if we plug in these things that we found using the exercise, this is b over x minus a over x over 1 plus, well, ba over x squared. And I don't like to look at fractions of fractions, so I'm going to multiply by 1 in my favorite form, which happens to be, in this case, x squared over x squared, which is going to give us bx minus ax over x squared plus ab. Okay, so at this point you might be wondering, this seems like a lot of work. Why are you massaging this expression? By massaging, I mean you're doing algebraic gymnastics.
Why do I recognize this form?
This thing on the right?
Yeah.
Maybe... Did we talk about the Cauchy distribution? Because if you factor out b minus a, this is x over x squared plus ab. Does this look familiar to you?
I almost want to say it does.
Okay.
Maybe I'm thinking of, like, I don't know.
Okay. Deja vu.
Weird deja vu. I don't know.
It also kind of looks like this is related in a kind of roundabout way. Do you remember the time dilation in special relativity? Time has this root 1 minus v squared over c squared. So it's a little different because here there's a square root, but there's a change of variables in relativity called the rapidity. And if you change variables in that way, this formula looks more like this formula with the x squared downstairs. Maybe that's what you're thinking of.
Nope.
Nope. Okay. Maybe just deja vu then. Okay. Good. So yeah, now you say, all right, this sounds like you're doing algebra parkour. How is this helping us solve the problem? Well, I claim that we get something which is nicer to optimize now. So well, my pen's fucking up and I'm trying to erase. Here we go. Good. So I've pulled out a b minus a, and I'm going to argue again. This is the thing we want to maximize. B minus a is some positive number. So if you want to maximize some positive number times this chunk, well, if you take this and multiply by a positive number, then the maximum of the product is going to occur at the maximum of the second piece, because this guy's just a constant. So now we can just maximize. Why did I say minimum? We want to maximize the angle. Look at me being schizophrenic. I want to maximize this expression over x. So I'll ask you. So there's no endpoints. I don't know if there's any places where the derivative is undefined, but the third place... Whoa, why did I write that? Find the minimum of the derivative. Now, ignore what I said. Find the minimum of this. But as we know, to find the minimum, one of the steps involves taking the derivative and finding critical points. Man, this is a poor slide design. Okay, anyway, so I want to minimize... Fucking... So I want to maximize this. What should I do?
I think we should take the derivative.
Good. What's that?
I'm trying to remember if L'Hopital's rule applies here. No. That would be equal to, not the derivative. Okay, I guess we're doing some very sloppy chain ruling.
Yeah, I think we'll need chain and quotient, yeah.
To remember. What am I trying to remember? Whatever, I'm just gonna quotient something. Yeah, I can't remember. Taking the derivative of a quotient as a named name. Just different quotient. There you go. Finally.
Oh,
no.
Your brain just did a free association there. That was like beat poetry.
What?
Never mind, I'm making a joke. Sorry.
I have no idea.
You've never gone to
Okay,
a poetry slam or heard people do this like beat poetry stuff?
No, I have not.
Okay. Anyway, the sentence you just said about the difference quotient sounded like it would be something someone would say at like an open mic poetry night, poetry slam or something. But
O- Okay, so we have just this is all over the bottom squared. This is going to be x squared plus ab minus x times
oh my,
2x.
sorry, I'll write that as soon as I reconnect my pen since it's skipping again. But you said
Woo!
x squared plus ab minus 2x was what you said?
Sorry, what was that?
Okay, so what you just told me was x squared plus ab, and then you said, what was it, minus 2x all over this thing squared?
Minus 2x. Yup.
Okay, so let's see, this is the derivative of the top times the bottom left alone, then we minus the derivative of the bottom, which is 2x, but also times the top left alone, right? So I think that should be 2x squared.
Sorry, what did I miss?
Maybe I misheard you. I thought you said the second term was minus 2x, but in the quotient rule,
I
this is derivative of bottom times top left alone. So derivative of bottom is
right.
2x. Yeah, that thing.
Okay, that makes more sense.
Okay,
And simplify the top to my knowledge. So it's
it's that
x
minus.
squared plus ab.
Yeah. Okay, so now we have the derivative. What do I do when I have the derivative in hand if I want to extremize things?
Well, can we factor out the negative on? No, we cannot. Darn. That was almost going to be fun. You were saying.
Well, let's see. So now we have the derivative. Then what do we do when we have the derivative if we're trying to find a max or min?
Well, we want to find some point where this equals 0.
Good. So this is critical point. Looks like we can multiply both sides by this thing in the bottom because this is positive. So the bottom's never going to be 0 because this is the sum. It's the square of a positive number. So if we multiply both sides by this thing, I think we get minus x squared plus ab equals 0.
Lovely.
And for the final stroke, which root should I pick?
Square root. Whoa.
Not the negative square.
Yep, maybe. That's so cool.
Good. So
Huh.
it's kind of cute.
That is weird.
It's not what you would expect, right? It's I don't know if I have the picture next. No, I want to go back to the picture though because it's I don't know. I have no geometrical intuition for looking at this. Why the square root of the product AB is somehow the best. I don't know if it's probably not actually true the way I've drawn it, but if this were square root of AB somehow, then apparently this is the one which maximizes the viewing angle. So it's kind of interesting that this occurs. By the way, this thing, you know, the average, or sometimes called the arithmetic mean. You've probably heard this. Arithmetic mean of two numbers means you add them and then divide by 2. I don't know if you've heard of this thing that we just found, this root AB, is something else called the geometric mean. And the difference is that instead of adding and dividing by 2, you multiply and then raise to the 1/2 power, which is square root of AB. So one way to phrase the answer to this question is say the viewer should stand at a distance which is the geometric mean of the height of the top and bottom of the picture. So, I don't know, I think it's kind of cute. Thoughts on Regiomontanus?
I do not have any thoughts, though I feel like there's one I should have.
What is the thought you should have?
I don't know. When was this geometric mean named?
When was it named, historically?
Right.
Or
after this.
don't. So you're asking like what year? Like when did people start doing this?
Yeah.
Yeah, it was probably. No, it couldn't have been the Greeks. I don't know.
Okay. So I was about to say, what if he came up with this name because it just felt right?
Oh, you're asking did they invent this word because of this problem? No,
Yeah.
that's not true. So the reason the reason people call this the geometric mean and this the arithmetic mean is related to arithmetic and geometric series, right? So if you have a series of numbers, say you start with a, and then the next number is a plus some other number r, and then the next number is r plus the previous one, so now it's a plus 2r, and dot dot dot. This is called an arithmetic series because you add a term each time. And if you have a series where you start with a and then start multiplying numbers, 8 times r, ar squared, and so forth, then this is called a geometric series. So I think the language around the means comes from the language from the two types of series rather than from the problem. But I could be wrong. I don't know the history of this that well. Good. That was a nice thought. Other thoughts?
I have no thoughts.
All right. I think that's kind of a fun problem. Maybe not as fun as the paper folding problem, but it's a pretty good one.
Did you say the paper folding problem was fun?
I thought that was very fun. When I was writing the solution, I enjoyed that a lot. Okay, so let's do another nice problem from our applications to physics. So this is straight out of chapter 1 of Kleppner and Kalenko. It's like the workhorse Physics 1 book. It's what I used for Physics 1 at MIT. It's the one I taught from teaching Physics 1 here. It's a very nice book. I even stole the figure. So anyway, here's the problem. Suppose you want to measure the acceleration due to gravity, right? So this is that g, which is like 9.8 meters per second squared, which we met. Suppose you're trying to design an experiment. Maybe you're on a new planet. You don't know what the force due to gravity is there, so you want to measure it. Here's one way you can measure it. You throw something upwards. So you start, man, this skipping pen is pissing me off, but you throw something upwards, and then you measure the time that it takes to pass two different heights. So here the problem is phrased pass 2 points in both directions, but don't get confused. This isn't a projectile that has an x direction and a y direction. This is you're just throwing something up, straight up along y. So when it says both directions, it means when it's going up and when it's coming down. So in particular, this is a height versus time graph, not a y versus x graph. We're not throwing a projectile in 2 dimensions. So you get this nice answer where you solve for g in terms of those measured quantities, and you get this 8 times the height over the difference of the squares of those 2 times, ta squared minus tb squared. And our goal is to prove this. So the first step, since I'm scaffolding these for you, the first step will be to either maybe remember from last time, or if not, we'll just rederive it. But if we throw something in a gravitational field, so maybe I throw something upward with initial velocity v0y or v0y, and there's a gravitational force mg downwards, then where is this guy at all times? What's y of t?
Thinking. Is this going to be... Well, no, we can't assume gravity. So I guess 2g times time equals yt?
2g time equals y. So this is where dimensional analysis helps us a lot, because g has units of meters per second squared, time has units of seconds, so the thing on the left side of this equation is meters per second, but y is units of meters. So,
right.
Yeah.
So.
Alright, so maybe we should rederive it. Let's rederive it starting from Newton's second law. So Newton's second law tells us y double dot, the acceleration, is the gravitational force, which points downwards, and that should be, my double dot is the gravitational force, which is minus mg, and we go ahead and cancel, which is why I didn't write it a moment ago. We immediately cancel this and get y double dot is minus g. So let's do one step and back it up to get y dot. When you anti-differentiate, what's y dot?
This is going to be half of g squared.
No. So the variable's t.
What?
G's a constant, and the variable that y depends on.
Right.
Maybe I shouldn't use dots. I don't think you like dots very much. This is d squared.
No, I have no problem with them. Just...
There we go. Okay, so treating g as a constant and anti-differentiating in t, then what should this be?
So this is just going to be negative gt.
Good. So we have the freedom to add a constant. What constant should I add so that when t equals 0, this thing has velocity v0y?
We should add... Wait, v0 comma y?
Yeah, I use the subscript 0 comma y to tell you two things. One, that this is the velocity at time 0, and two, that it's a velocity in the y direction. I don't actually need to do that in this problem because there's only one... Ah, damn it. There's only one direction. There's no x and y. But I usually like to have more descriptive subscripts. So anyway, that's just my bias.
v0 then.
Yeah, let's call it v0, I guess. Good. All right, one more step. So anti-differentiate again. Assume it starts at 0 height. So what's y of t?
So this is going to be negative 1/2 g of, well, negative 1/2 g t squared plus v sub 0.
So let's see, I want to take the derivative of
Our initial position of y.
this should be v0 t.
Did not hear what you said over the sum home.
Oh, sorry about that. Did you say v0 or v0 t for this piece?
I said v0.
Okay.
I see.
Yeah, we want this when we take the time derivative
Yeah.
of that thing. Good. Okay, and then as you say, we can add 0, but that's the initial height. Okay, so this is...
Units.
What do you say?
It looks like all the units make sense. Meters per second times time.
Good, yes. You are developing the habits. Good. Meters per second times seconds. Good, 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 good. All right. You are learning to make the right kind of comment, whereby the right kind of comment I'm being very prejudiced in saying the types of comments that I like to make when I solve these problems. Okay, good. Units work. This is indeed correct. So this gives us the height at all times. So, okay, so how do we use this when we look at the picture? Well, the first thing we're going to do, since note that the thing we're trying to prove that g is equal to, this thing only knows about HTA and TB. It doesn't know about V0. So that's very interesting, actually, that this this particular combination of quantities doesn't depend on how fast you're throwing it. It's just independent of V0. But anyway, that's true. If our answer can't depend on V0, we better get rid of it. We better write down an equation that will allow us to eliminate V0y. So I will ask you, reproducing the equation we had a moment ago, y of t is minus a half gt squared plus v naught t. How can I use this point here, which is the observation that y at time ta is back down to 0. By the way, for convenience, I'm choosing our origin here. So this height a is going to be 0. It just makes life easier. Okay, so how can I use this to get an equation for v0?
Oh, wait, it's straight up equals y of ta. Because y of 0, wait. No, let me think. Why did we say y of 0?
Why? Because y is a function of time. So when time is 0...
Oh, right.
Yeah, so this is the y of 0. Actually, I don't know why I really wrote it like this, because, I mean, this equation is true, because it's at height 0 at both of those times, but we don't actually use both of those conditions, we just use the second half. That's the only one that's useful. The first one's trivial. Or said differently, now that we have this equation that tells us what height the object is at each point in time, what does it tell us if we plug in ta to this equation and demand that the result be 0? What condition do we get?
It tells us that the constant must also be 0.
The constant must also be 0. What do you mean?
Everything must be either 0 or the negative. And well, TA is, I assume TA is positive, so I think.
Right, so t is positive, so indeed I think we can cancel it, but then this gives us an equation for v0, right? This is telling us 1/2 GTA minus 1/2 GTA plus v0 equals 0, and what we're trying to do is get an equation for v0. So when I solve this for v0, what in terms of known quantities, well, known quantities, in terms of g, known quantities in g, what do I get?
Could you say that again? The sump pump exists.
Okay. I mean, I realized when I was asking the question that I was just asking you to add 1/2 GTA to both sides of this equation, which is almost too embarrassing to ask you. So anyway, what I was explaining is that the condition that y equals 0 at time ta gives us this relationship, which allows us, recall our goal was to eliminate v sub 0 in favor of other things. So we have used this equation and solved for v0 to get this expression. v0 is 1/2 GTA. Is that clear, or was the motivation for the step a bit murky?
It is understandable.
Okay.
Also, no GTA here.
Oh yes, Grand Theft Auto. Maybe I should have written it as TAG in order to avoid that. Good. Okay, so that's one thing. And indeed, as we just said, we get v0 is 1/2 GTA, or TAG, if you will. Okay, so now we can use this. I'll give you the hint which makes this problem easier than if you try to solve it a different way. We can use symmetry in the height time graph. So by symmetry, if we cut this guy in half, well, let's see, this, I don't know how to draw it. The two regions here, when the guy is going up by h and then down by h, so the sum of these two regions is, just by geometry, looking at the length, well, the sum of these two regions is what you get by taking the whole time TA and cutting out the TB. So the sum of these two regions has to be TA minus TB. But by symmetry, the two are equal. So that means that, kind of, maybe it's easier just to look at 1/2. That means that this time, when the guy goes from height 0 up to height h, this guy must be TA minus TB over 2. So that's a useful observation, because now we know that when you plug in that value of time to our function y of t, when I plug in that value of time, TA minus TB over 2, as we've drawn it, this thing is at height h. So we're going to use that to nail down the problem, actually. That's the last ingredient we need. So, by symmetry, indeed, y at TA minus TB over 2 must be h. And we also know the previous result, which is v naught, is 1/2 g times t sub a. And again, I'm going to reproduce our favorite dynamical equation here that gives us y at each time minus 1/2 gt squared plus v0t. Okay, so now I'll ask you, what should I do? How can we combine these ingredients to solve for g as we wanted?
Remind me, what is h here?
H is this known height. So we were trying to measure g, and we said, all right, I'm going to throw something up, and I'm going to measure the time that it takes to pass, this given height on the way up and this given height on the way down, right? So h is known. Our answer can contain h. Oops.
Of course, some pump happens. Okay. Uh,
Did the pump interrupt you?
no, and
Well, maybe to start we should just expand out this equation, right? So what does this give us?
that is equal. Let's see. We could straight up insert TA minus TB over 2 into our y of t, but I don't think that would be very useful.
Well, there's not much else we could do. I mean, we have this equation, we know y at each function of time, so I think we either have to plug it in or we have to try to do some gymnastics first. Um, the hint was set up in such a way that inserting this expression would actually work out in a reasonably nice way. So maybe we should just try it. So if we do that, what should I write for the right side when we insert that?
It's going to be negative 1/2 begin quantity, excuse me, negative 1/2 g begin quantity, TA minus TB over 2 squared plus V0, well, not V0, 1/2 GTA times T, where T, once again, equals TA minus TB over 2.
Good. Sorry, damn it, the pen fucked up while you were saying that, but I was still listening. I think it was right. So you said to put this junk in here and square it, and then I think you said replace V0 by a half GTA, and that whole thing is multiplying T, but T is this junk. Right, so TA minus TB over 2. Alright. Nice thing is that now these guys all come with a 1/2 g overall. So I'm going to factor out the 1/2 g. And inside here, I'm going to do some algebra for you and square them, and distribute this guy. And then I'll ask you to simplify. So when I square this guy, I'm just going to FOIL. So
Could you just factor out the TA minus TB over 2?
can I factor out? Yes.
Does that help us at all?
Well, let's see. We would still have to solve for g. So you could write it that way. Yeah, you could do that, but at the end of the day, I think we need to cancel the like terms here. Like, yeah, that's correct. Let me say it differently. That's correct. If you factor that out and solve for g, the thing you've written down will be correct, but it will look prettier if we cancel like terms between these. And to cancel like terms, we should do the square, and we should distribute the TA, because you can see we're going to get a TA squared here and a TA squared here, and they might combine in a nice way, right?
Okay.
So I'm going to switch the order, so I'm going to write this term first. So I pulled out the half g, then I'm left with a TA squared minus TA TB from distributing the TB. This guy's all over 2, I think. Is that right? Yeah, I think that's right. Okay. Then in this term, well, let's see. Now it's all going to be over 4, because I'm squaring this guy. And in the top, well, we've been able to FOIL since kindergarten, so this is TA squared minus 2TA TB plus TB squared. Okay, so do you see what simplification happens now?
This is not a hard question, I know.
Well, what should I do to combine fractions with different denominators? Different way to say that question.
Multiply the 1 on the left by 2 over 2.
Good.
Yeah.
Multiply by 1, the only trick we have. Good. Half g. So this, man, this skipping pen. Maybe I need to buy a new tablet. Ah, what the fuck are you doing? Multiply by 2 over
Beautiful.
2. Yes, apologies for the laggery, but okay, so when I multiply by 2 upstairs, I get a 2TA squared minus 2TA TB, and this is a... Oh, I've made a sign error. Sorry, this should be a minus, right? Because there was a minus 1/2 g in front of this first term, and the second term here came from squaring this guy. So I've only factored out the 1/2 g, but not the minus sign. So it should actually still be a minus carried here. Good.
I was thinking about that, but I didn't even catch it.
Good. You should always interrupt me when I do stupid things. But okay, so make sure you're clear on why I'm going to switch the sign on all of these, right? Because this is minus this quantity, so I'm really distributing the minus sign across all three of these guys when I write this out. So when I do that, that gives me the minus on the TA squared for the first guy, gives me, of course, minus TA squared. The minus sign hitting the minus 2TATB gives me a plus 2TATB. And the minus hitting the TB squared is, of course, minus TB squared. And this is all over 4. Okay, so now there's some miraculous cancellations. So what do I get inside the brackets when the dust settles?
We're going to have TA squared minus TB squared?
Looks right, yeah, because these guys cancel. 2TA squared minus
Oh,
TB.
wait, yeah.
Yeah, what you said was right, yeah. TA squared minus TB squared. All over still 4.
Yup.
Alright, so now we're effectively done, because this whole thing was h. All we have to do is solve for g, but to solve for g, well, a half and a fourth give us an eighth, so I'll multiply both sides by 8, there'll be an 8h here, then I'll divide by this difference. So the implication is that g will be, skippy pen, g will be the 8h from the 4 and the 2, all over TA squared minus TB squared. So that's it, actually. So that's what we wanted to prove. And if you wanted to, this is a classic experiment in a first-year physics course. You might use a light gate or something, which is a little machine where it has kind of these two heights, and you have a stand here that's shooting kind of lasers at those heights. And when an object breaks the laser, this thing registers a time. So you just throw something up, and it comes up and comes down, and this thing's connected to a computer, and it spits out on a spreadsheet what was the time where it broke the first laser, the second laser, the second laser, the first laser, and then you just go in your spreadsheet and use, Excel functions, take, h times this height, divide by the square of the difference of the times, and you get an answer for g, which will be roughly 9.8 meters per second squared. If you're like me, you're kind of shitty at designing experiments, so you'll get a wrong answer, which is like 9.6 or 9.9 or something, because you were not very accurate, and so that's why I decided to be a theorist and not an experimentalist. But anyway, so that's the flavor of what one would do for problems like this. Thoughts or observations?
I muted myself again. That's my observation.
And you have this problem.
I mute myself because of the sump pump. I don't know why it exists. It's very loud.
Kill it. Kill it with fire.
What if it's already dead?
Dead inside. Good. Happy with all this then?
Yep.
Nice. Okay. I think that's fun. Okay, so this is what we just did. Okay, so now I want to do a little bit more with these limits at infinity and limits of infinity. So I should tell you what these two prepositions mean, because it seems like I'm distinguishing between them. But first, just to remember what we did last time, I like this cute little, I guess, sanity check for L'Hopital's rule. So recall that L'Hopital's rule tells us about limits of a quotient where the top and bottom both go to 0. So clearly in this quotient, which is the usual difference quotient, which defines, if it exists, f prime at x, this is a quotient of two terms, or two expressions, which both go to 0 when h goes to 0, right? Because clearly h goes to 0 on the bottom, and at the top when h goes to 0, this becomes f of x minus f of x, which is 0. So in principle, we should just be able to apply L'Hopital's rule to the difference quotient inside, thinking of this, as a ratio of two functions of h, right? Some function, I don't know, f1 of h over f2 of h. We're just thinking of these as functions of h now, and applying L'Hopital's rule. So if I do that formally, what do I get?
Are you asking for the difference quotient?
No, I'm asking you apply L'Hopital's rule to this limit of a
Okay.
quotient.
Well, this is going to be equal to, I guess I'm going to chain rule. Should I?
You'll need a chain rule for this guy, right? So
Okay. So this is going to be f the entire the entire top side I need to think about. This is going to be f prime of x plus h times h minus f prime of x.
well, let's be careful. So what does L'Hopital's rule tell us? So L'Hopital's rule tells us that if you have, I shouldn't use x. Let's be clear. Limit as y goes to 0 of f of y over g of y. I should put in the conditions if, f and g go to 0, then this thing is the ratio, the limit of the ratios of their derivatives. So in the problem we're doing, what is y? What is the variable we should be taking the derivative with respect to?
H.
H, good, okay. So what's the derivative of f of x with respect to h?
Zero, I guess.
Good, so that's 0. And now in this first term,
Struggling.
what'd you say?
Struggling.
No problem. Good, so in the first term when we chain rule, I agree we take the derivative of the outside, which is f prime at x plus h. What should I multiply by, which is the derivative of the inside with respect to h?
Say that again?
So when you chain rule this first term,
Oh.
what should I multiply by? What's the derivative of the inside?
This is multiplied by 0 plus h. What? No, 1 plus h. No, x is not the thing. It's 0. But what am I getting wrong there?
Well, I think this should be 0 plus 1, which is 1, right?
Oh.
ddh of x is 0, ddh of h is 1, right?
You see, everything breaks when you change the variable name.
Yeah, this is why we had that one session that I think you were very unhappy with me after, where I was beating a dead horse and we were taking derivatives with respect to different letters, and there was an a plus 3 and x plus 3, and taking derivatives with respect to x plus 3, and you were thinking, okay, what life decisions have I come to that I'm being forced to do this? But as you see, it's quite important not to confuse these. Okay, what's the bottom?
Remind me, are we... Okay, we're taking the derivative of the top and the bottom individually, right?
Yeah, that's how L'Hopital works.
And this is just going to be all over 1, right?
Good. Okay. So what is this telling us? L'Hopital's rule applied to this difference quotient. Limit h goes to 0 of f prime at x plus h. So if this equation is true, what is the word that we use for this? What is this condition?
Noises. Sorry, what was the question again?
So I'm asking you to explain what is the result that we just got. What is the interpretation of this equation?
It basically told us nothing. Just told us that this... Oh. Is a derivative no, not continuous.
Yeah,
Thinking.
I think that's what we want, right? The statement that you have some function, f prime, and the value of that function, which is here f prime at a point, is equal to the limit as it goes to the point. So we have a word for that. The word for that is continuity, right? Continuity. So this is the statement. It seems like we're getting something for free here, because it seems like we assumed nothing about this function, and then we've just proved that the derivative is continuous. Right, so it seems like we, quite the opposite of getting no useful data, it seems like we got something for nothing, continuity of the derivative. So the secret that why we didn't actually get something for nothing was in the assumptions of L'Hopital's rule. So when we prove L'Hopital's rule, we assume certain things, in particular that I think f prime over g prime exists on some interval around the point in question, so here it would have to be on some minus delta delta interval, except possibly at 0. So except possibly it's 0. So we assumed a little bit by applying L'Hopital's rule, which is that this ratio exists on an interval, which means, in this case, that the derivative exists on an interval. So we didn't quite get something for nothing, but we got something very cheaply. And this is related to the observation we made last time that derivatives, when they exist on an interval, can't have point discontinuities, right? So if you assume that this f prime exists on an interval, you're guaranteed it's continuous. You get continuity of the derivative, which is kind of nice. But anyway, this is not related to the limits at infinity. It's just kind of a review of stuff that we're doing with L'Hopital's rule generally. So good. Thoughts on this?
I have no thoughts.
Cool. Okay. So indeed, as we said, top and bottom go to 0, so taking the derivative and using the chain rule on x plus h, this is a continuity statement, which we got out of the assumptions of L'Hopital's rule, effectively. Okay, so you might say that's kind of useful. You can get some interesting results using this L'Hopital's rule. I wonder if there are other cases when you can take a quotient and then take a limit of that quotient and it will equal the quotient of the limit of the derivatives. So there are other versions of L'Hopital's rule which are true, and I will write them even though these are formally meaningless at the moment because we haven't defined these symbols. But if f goes to 0 as x goes to infinity, and g goes to 0 as x goes to infinity, so graphically you would think of this as what we call a horizontal asymptote, right? So this is a horizontal asymptote. It's just the statement geometrically that as you go further and further to the right, that this function f gets closer and closer to 0, right? So this idea of getting close to 0 as x goes to infinity is the analytical way of expressing this geometric notion that it has a horizontal asymptote that tends to 0. So if f and g have horizontal asymptotes, then, as it turns out, their quotient will also have a horizontal asymptote, which is given by the horizontal asymptote of the ratio of their derivatives. So it's another version of L'Hopital's rule. There's another thing you could do. What if the limit as x goes to a of f equals infinity, plus or minus infinity? What does it mean for a limit to be equal to infinity? Well, it means nothing at the moment, again, but we will define it. What this is expressing, as you've probably guessed, is the notion, say, of the tangent function. You know, the tangent function is sine over cosine, and cosine blows up. Cosine goes to 0 at pi over 2. So that means that the tangent function near pi over 2 goes to infinity. It blows up from one direction, comes up from minus infinity, so it blows down from the other direction. This thing is what we would call a vertical asymptote. So we would like a way to, I mean, it's all very nice to draw pictures, but if we want to prove things about these, we really need to convert the pictures into the serious machinery of epsilon deltas. So we should define what we mean by these two things, which I've switched the order actually. The thing on the bottom, where the limit quote-unquote equals infinity, which is a vertical asymptote, for short I will call that a limit of infinity. The value of the limit is infinity, so it's a limit of infinity. And the first one, the horizontal asymptote, I will call limits at infinity. So it's kind of like I think of this as x getting close to infinity, so it's at infinity. These are just the words. Questions on the words?
I assume that this definition does not tell us anything about dividing by 0.
No, but it will allow us to evaluate so-called indeterminate forms, which look like 0 over 0, sometimes called an indeterminate form. So a finite number divided by 0, like 1 over 0, that is just undefined. So indeed, we can't divide a finite number by 0. But sometimes in a calculation, inside of a limit, you get something which formally, if you just plugged in numbers, would look like 0 over 0. So again, that's undefined. Technically, it's an indeterminate form, but it really means somewhere you made, some sloppy calculation. It means that you did something you shouldn't, and you got some nonsense. But if you had done something correctly, there actually would have been a honest-to-God number that comes out, like 5, or, 12 or something would come out. So the whole point of this unit is to think about ways of figuring out what this indeterminate form 0 over 0 should have been and kind of working backwards to extract the correct number instead of, this weird thing you get from sloppy calculation. I don't know if that makes any sense. What do you think?
I think I've actually had the 0 divided by 0 thing come up quite often, and I've never known what to do.
Yeah, it's tricky. I mean, you could just do a very simple-minded example to see why 0 over 0 could be associated with different numbers. And the stupid thing is this. What is the limit as x goes to 0 of x over x? Well, of course, x over x, whenever x is non-zero, right? Again, I've said this probably 10 billion times, but the value of the limit is insensitive to what happens at the point. So this thing away from that point is always 1. But if you did something sloppy, where by sloppy I mean uh, instead of using epsilons and deltas, just plug shit in, which will always get you into trouble. If you were being sloppy and said, "Oh, I don't give a fuck about limits or epsilons or deltas. Whenever I see a limit, I'm just going to plug in the numbers," you get 0 over 0. So, from this perspective, 0 over 0 apparently is equal to 1. But I could have done, something else which is very stupid and just say, what about the limit as x goes to 0 of 2x over x? Well, this is kind of almost trivial, but obviously 2x over x away from 0, you cancel the x's, this is 2. But again, if I were being sloppy, I would say I'm plugging in 0. 2 times 0 is 0, so the top is 0. The bottom is 0. And if I'm being sloppy, I would have said, well, these two things are equal. 0 over 0 has to be equal to 0 over 0. If I were doing that, if I were being sloppy, then I would get 1 equals 2, which is bad in most countries. So the getting 0 over 0 problem, which you noted comes up often if you don't go right down to the bare metal of epsilons and deltas, then you get these indeterminate forms which should have honest-to-God legit numerical values, but they just look kind of silly because somewhere something went wrong. Good comment. Other thoughts?
I have no further thoughts.
Sweet. Alright, let's do some things. Okay, so we should define a limit of infinity. So let's just think, how did we define ordinary limits way back in the day? So we said there's some function, maybe, I don't know, it doesn't have to be defined here, but it's supposed to get very close to that value as we get close to a. And then I said, well, how should we make those words close meaningful? And I argued the way to do it is to say, well, to say precisely what it means that you can get arbitrarily close to a point, you should say the following words. However close you want me to get to that point, I can guarantee a way of getting that close to the point by making your input sufficiently close to a. That was the whole point of epsilon deltas. So now what does it mean to be, we have to express a version of this for limits of infinity. So the first thing is, well, okay, now this point L apparently equals infinity. So what does it mean to be close to infinity, right? If I'm saying you want to get arbitrarily close to infinity, I need some idea of what does it mean to be within distance epsilon of infinity. That doesn't make a lot of sense. But if you think about it for a moment, you can see that a reasonable way to fix that problem and generalize is to interpret the words close to infinity as bigger than some number, maybe a huge number. So bigger than, I don't know, n. So I say you're kind of close to infinity if you're always bigger than 100. You're a bit closer to infinity if you're always bigger than 1,000,000. You're even closer to infinity if you're always bigger than 10 to the 900, whatever. So if you believe that, then maybe we should define the limits at infinity using the same epsilon delta technology, but replace the epsilon part by saying you can get bigger than whatever big positive number you want. Okay, so if we do that, we would say the limit as x goes to a of f of x equals infinity if for every big number n, which is positive, there exists some delta greater than 0, which is this part's unchanged. Delta is the x part, the input. So that if my input is delta close to a, then my output is bigger than n. I can make the output as big as I want by getting closer and closer to A. That's the definition we'll use. Okay, so now I would like to also have a throwback, because when we first did limits, I made a big deal about the following observation. When we did the epsilon delta definition, I said, be very careful, because we are defining this entire collection of symbols. This is just like a Python variable where this entire collection means this sentence. The limit as x goes to a of f of x equals L means this giant thing that for every epsilon there's a delta such that this implies that, blah. And I said, don't think of this yet as a number on the left equals a number on the right. Think of this as shorthand for a big collection of symbols. Then after that, I said, now we can prove that if this is true, there's a unique number k with this property, and we can now interpret this equation in a second way, which is now not just the entire collection of symbols, but now we can interpret the left side and the right side separately, right? So we interpret the limit as x goes to a of f of x as one number, so that's a number k. We interpret the equal sign as the usual equality of real numbers, that's L. So now this is saying there's a number k which equals a number L. So two different interpretations. For finite limits, they were equivalent. Why did I stress that? Well, one, it's just, I mean, this is just correct. You can't interpret something as an equality of two numbers until you've proven that the left side defines only a single number. So one reason for emphasizing this was just intellectual honesty. But the second reason is that now, if we're going to include infinite limits, we no longer have the option of doing two, right? We can't do this. Why can't we do that? We can't say the left side of this equation is some number, and the right side of this equation is some number, and those two numbers happen to be equal. Can't do that anymore. Infinity is not a number. I want to be very, very clear here. When I write this, I am not writing an equation between two real numbers. Infinity is not a number. Can't stress that enough. People make a lot of stupid mistakes because they treat infinity like a number. This is not an equation between numbers. This is only in the sense of option 1. This entire object is like a Python variable for this long sentence about n's and deltas. So you cannot think of this as number equals number. It's just a big bucket shorthand. So, okay, I'm beating a dead horse, but I just want to be very careful so we don't do sloppy things. Is this whole thing sensible to you?
Yes.
Okay. Good, good. Alright, so if we're happy with that, what about limit at infinity? So this will be somewhat less subtle, because now we just need to change the part about being delta close to something. So if I want to tell you that f of x goes to, I don't know, some finite number a, maybe it doesn't have to be 0. If f of x eventually settles down and it approaches a as we go to infinity, how should we say that? Well, we should say same thing. If this is a, then I can make the output of this function arbitrarily close to a for any epsilon. I can make it close to a by going far enough to the right. What does far enough to the right mean? Well, maybe we should say pick some big number, which this time I'll call m, and say, well, if you're far enough to the right, which means x is bigger than m, I know you're going to be that close to a, right? If you want to be within, I don't know, 1/1000th of a, I'll find some number, maybe it's a billion, and if your input is bigger than a billion, you're always going to be within 1/1000th of a. That's the idea. So if we can do that, we would say the limit as x goes to infinity of f of x equals L if, again, for every tolerance epsilon, there exists a big number m, so that when the input is bigger than m, so we're switching where the big number is right now. Now the big number is on the input side. The big number is bigger than m, then f of x is going to be within distance epsilon of L. Oh, I call this, sorry. Picture doesn't match. This should be L. Good, so this defines a limit at infinity. Pretty obvious generalization. If you want a limit at minus infinity, you just pick a negative number m, so that whenever x is less than the big negative number, again, you're within distance epsilon of L. That's fine, okay. So this expresses, as I said before, a horizontal asymptote. That's the idea. So anyway, I will make one more caveat again. So we're defining I mean, you can run the same argument, but this time it actually works if you interpret this as one number on the left and one number on the right. So you can interpret this in either way 1 or way 2, but I hasten to add that if you're interpreting it in way 1, whichever one was the one with a number, I guess way 2. If you're interpreting it in way 2, where its number equals number, you have to be very careful to say there is a unique real number defined by the left side of this equation, but that number has nothing to do with this thing, this symbol at the bottom. The symbol x goes to infinity at the bottom does not mean that x is approaching an actual real number infinity. We're just using this as shorthand. Just using this as shorthand for, you can make x bigger than some m, and it's going to get you epsilon close to L. So I'm using the symbol infinity. That doesn't imply it's a number. It's just shorthand for this collection of sentences, this collection of symbols, I guess. So, you should just think of it. This is the thing which is meaningful. Okay, good. Thoughts on this?
So it seemed that the focus on the fact that the limit here, shorthand, is even more important than last time.
More important than in the of infinity one?
Well, than chapter 2.
Oh, for finite limits. Yes, yes. Oh, it's much more important. Yeah. Maybe that's an argument for even why one should do infinite limits already in chapter 2, because then you would not be wondering why I was making this big deal of emphasizing the shorthand. Because, yeah, it's much more important here, but I don't know. I think it's just good to be careful about what it is you're defining in either case, but here it's important that we don't want to get in trouble for writing infinity when we don't know what we're talking about.
Oh, I guess I'm kind of already doing that and accidentally did that with my calc class right now.
Ooh, tell me, what did you do?
We're talking about end behavior, whatever that means.
End behavior? Oh, like horizontal asymptote, slant asymptote, that sort of thing?
Yeah, finding something as it goes to positive infinity, like 3x squared over x squared or something.
3x squared over x squared. Ah, okay, yeah, so this guy, you can make it more interesting and say, 3x squared plus x over x squared minus 1 or something, and of course you just look at the leading terms, this thing's going to go to 3. Right?
Lovely.
What'd you say?
Makes sense somehow.
Actually, maybe I should just say, the reason that we're developing all these limits at infinity is so you could prove this, right? Because right now, if I asked you to prove the end behavior of this thing, which you're doing in your calc class, if I asked you to prove that the limit as x goes to infinity of this thing equals 3, you wouldn't be able to do it, even though we have this expression. But when we have the new super version of L'Hopital's rule, which says that if top and bottom go to infinity, the limit equals the limit of the derivatives, then, oh great, we can just apply L'Hopital over and over, right? This is the limit as x goes to infinity of the ratio of derivatives, which is 6x plus 1 over 2x. You can apply
That's cool.
Yeah, you can go as many times as you want, right? So this is 6 over 2, which is 3. Good. So the super L'Hopital gives us a proof of the shit that you are being spoon-fed in your calculus course without any explanation, which is that to find the end behavior, you just look at the highest power and divide the two numbers.
And suddenly I have this feeling again, like I'm being cheated.
Yeah, you're being swindled. That's the entire enterprise of high school, is to swindle you. Good, very good comment. Other thoughts?
Identical feeling to the fact that we couldn't do matrices because everyone else was too slow in Algebra 2.
Yeah, that frustrated me a little bit. Tried to write it into your GIEP, you said, but that didn't work.
Right.
Well, by the way, if there's any other things like that that you feel swindled, that you feel like you should know and are not being told, let me know and we can bake that into another matrices thing or something.
Will do. I'll tell you probably tomorrow. Okay, I need to do my schoolwork today since I'm not home all day tomorrow. Awesome.
That sounds painful, but okay, well, good. Then I will try to finish so you can do your silly schoolwork.
You still have 45 minutes and 4 slides.
Yeah, I don't know if we'll use all the time today, but today was kind of a leisurely pace, but...
Yeah.
Okay, good. So let's try to prove something using those definitions, right? So using our brand new definition, actually we'll use both of them, right? So this one will use both a limit of infinity and a limit at infinity, right? So there's both of them being in play. So once my pen stops skipping, I'll just draw what we're talking about. The proposition is that if f of x is just this monomial, right? X raised to the power n for some positive integer n, maybe it's like a square or a cube or, I don't know, some quintic, whatever. Um, but whatever it is, I don't know why I drew it like this because it can't really look, you can't have roots like this if it's a monomial, so I really shouldn't have drawn it like that. I'll draw it like, I don't know, like this. Maybe this is supposed to be x to the fourth or something, who knows. But anyway, I think it's pretty clear that if you take a number and raise it to a positive power, then this should have the property that as you go to infinity on the x-axis, this should go to infinity on the y-axis. That the limit as x goes to infinity of f is infinity. Okay, and just to remind us of the definition, what does that mean? Well, we need both of them. So we need that for every big number n greater than 0, and I have to switch to the other one, for every big number n greater than 0, there has to be another big number m greater than 0, so that whenever x is bigger than m, the output f of x, which is here just x raised to the power little n, the output has to be bigger, going back here, than n. So this is what we need to prove. So I'll write the definition, then ask you how to do it. So want to show, or by the definition, what we need to prove for every n greater than 0, there is some m greater than 0, so whenever x is greater than m, we have x to the power n is greater than capital N. Okay, so what should I do?
I guess we want to find some, well, I don't know if we want to find or define a value like we usually do with epsilon delta proofs.
Yeah, the logic is the same. In an epsilon delta, because whenever there's a for every in a proof, you have to start by saying, all right, hand me a value. So just like, for every epsilon greater than 0, you begin a proof by saying fix an epsilon, or give me an epsilon, or let epsilon greater than 0 be given. So we'll do the same thing here. Let n greater than 0 be given. Good. Okay, now I have to tell you how to pick an m. So what do you think we should do to find an m?
For whatever reason, I'm thinking along the lines of um, kind of working backwards and like m to the n equals n, and then solving for
Equals n.
upper n.
Ah, okay, yeah. When you say work backwards, you're saying, okay, so we want x to the n to be bigger than n. So what choices of x would give us that? And so you're saying something like maybe, yeah, okay, let's do this. So, well, first step. So the equation you just told me, start with m to the n equals n. Solve this for m, because we're trying to cook up the m. So what does this get if I solve for m?
I believe that this is going to be n times log m equals log n, and in turn
Ooh.
log m equals log n divided by n.
So, good. Log m is log n divided by n, and we want to get rid of the log, so what happens when I take, say, an exponential on both sides?
Sorry, say that again.
So I'm trying to undo the logs in this equation. So I take e raised to the power of both sides, right? E raised to the power of both sides kills the logs.
Ah, that makes more sense.
So in the
Well,
last,
it's cool.
okay, so I'm going to write the right side in a particular way. E to the log n, this is power to a power, right? 1 over n. Okay, so then what does this give me?
It's going to be e to the log n equals n to the power of 1 over lower n.
Yeah, n to the power 1 over little lowercase n.
Or this might be something like n root of n.
Yeah, good. The nth root.
Oh.
So in fact, we could have done this without the logs if we just started from this equation and took the nth root, both sides, nth root of both sides, then we would have
But
found m is nth root of n, right?
I guess it kind of seems cheaty, but it also works.
Yeah, I mean, the log version is actually a bit more rigorous because, I mean, we're being a little sloppy. I mean, we're assuming n's a positive integer, but maybe you would have an eye to generalizing this to other powers, so you want to be careful about, does it make sense to take a -1 root or something? But at least in this problem, we're totally safe, and you could just take nth roots. But good, in fact, by going through the log thing, you've actually supplied a proof that the nth root is well defined, assuming you know log is defined, so that's a nice thing to have.
Lovely.
Okay, so it sounds like what you're telling me from this working backwards sort of exploration stuff is that if I pick m to be the nth root of n, then certainly whenever x is bigger than that m, x to the power n is greater than n, almost trivially, just by raising to power. So let's pick it. So let's pick m equals the nth root of n. Now I have to convince the reader that this is true. So whenever x is greater than m, which is here the nth root of n, we have, by raising both sides to the nth power, which preserves inequalities, we have x to the n is greater than, well, the nth root of n to the nth power, which is n. But this is the definition of the series of symbols limit x goes to infinity, f of x equals infinity, which is what we wanted to show. Oh, a period outside quotes. Good. Okay, so geometric, I mean, maybe this is obvious if you draw a picture, but it's good to prove. So we know that monomials tend to infinity at infinity. Their end behavior is, to blow up. Good. Thoughts on this?
And I assume that this is, oh, that's cool. So this is all monomial n. So even linear functions approach infinity at infinity.
Yep. Good. Yeah, so this works for lines.
Oh, that's cool.
Very good. Doesn't tell us about the slant asymptotes, though. The slant asymptotes are what you get by ratios of functions, rational functions. So this is just monomials, not rationals, but that's fine. We could do rationals later. Good. Other thoughts on this thing?
I have no further. Actually, what would we do if there was a coefficient?
Oh, good.
Barely be changed?
Yeah, so all we would do is say whenever x is greater than m, we would choose a different value of m, which is probably, what, nth root of n over a? Is that what I want? Because then, let's see, f of x, oh, you'd have to be a little careful about sign. A has to be positive. If a were negative, we can run the proof, but then we have to change it, right? Because then it goes to minus infinity, right? So if we had a positive coefficient, then we would just say, okay, f of x is ax to the n. So whenever x is greater than the nth root of m over a, then when I plug this in and raise it to the nth power, then f of x is going to be bigger than, well, m over a times a gives me an m. So for positive a, the proof is almost unchanged. You just change the pick for m a little bit. If a is negative, then you have to switch the proof. You have to pick a negative number, but otherwise the proof's the same. If a equals 0, then this isn't even true. If a equals 0, it's obviously the 0 function. So I think that handles all choices of constant. Good. That was very good. You're good at making the comments. Like, every presenter talking about math is hoping when he presents something, the comments or thoughts are going to be like interesting ideas that extend what he said, right? Like, how do I generalize this? How would this be different? When would this break? What happens if I remove an assumption in the proof? Is there, some application of this, or is there some special case I can consider that's interesting? So comments that, go in that direction are just, I don't know, I find they're more exciting. They make the discussion a lot more fun. So I think you're getting good at this. I appreciate these comments.
And I feel like it is only marginally related, but how would we talk about this in terms of some n minus 1 being added onto f of x?
Some n minus 1.
Well, plus x to the power of n minus 1.
Oh, okay, so you want to generalize to
Going
x.
all the way to polynomials.
Yeah, good, good, good. So xn plus, I don't know, xn minus 1 plus dot dot dot. So yeah, so there's a trick. I guess you could just do this if all of these are positive. Yeah, yeah. So for the proof here, we could actually just run through the same argument, because if you add any set of, say, positive coefficients, I guess that's the easiest one. So let me solve an easier version of your question. So if I have positive coefficients a n x n plus a n minus 1 x n minus 1 plus dot 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 plus a 0, then actually the same proof goes through, because if x is greater than square root of the big number we need, what was it, n over a n, then f of x is going to be, well, we're only adding positive numbers to that first term. So if you only add positive numbers to this thing, it can only get bigger. It can only get bigger than what I would get by considering this term alone, which by plugging in and raising to the nth power, this is bigger than n. So the same proof works if they're all positive, right? Positive things. Then you say, okay, what if some of these are negative? Ah, good. Okay, so then there's a trick. Then if some of these are negative, we do the dividing out trick. So we do f of x, you just divide out by the highest power. So this is going to be, let's see, do I want the biggest one? Yeah, so I'll divide out by x to the n, so I'll have a n plus a n minus 1. This is, how should I write this if I'm dividing out by this? Yeah, I guess I should, I don't know. Okay, I'll write it like this. F over x to the power n. Here we go. I'll write it like this. So a n minus 1, well, what's x to the n minus 1 divided by x to the n? Well, there's a 1 over x here. And then there'll be an a n minus 2 times 1 over x squared plus dot 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 down to the a0, which will be over an x to the n. Then we're going to take limits of both sides. Now, I haven't proven this yet, because this is where you need the super L'Hopital's rule that works for limits at infinity. But you can kind of see we use the L'Hopital for this side, this quotient on the left, and take derivatives. And you can take enough derivatives until the xn goes away, and you're just left with some derivatives of f. On the right side, as x goes to infinity, well, I haven't proven this yet either, but you can show that as x goes to infinity, 1 over x goes to 0, kind of obvious. 1 over x squared goes to 0. 1 over x to the n goes to 0. So you just kill all these 1 over x pieces, and then you get this thing as a constant. If this thing is a constant, okay, well, after I do my L'Hopital a bunch of times on this, then this means roughly that the limit, I'm being kind of sloppy here, but you can see that if the limit of the ratio of these two things is going to end up being some constant, then that means if I can multiply across, that means the limit of f, the guy I'm interested in, has to be the same, up to some constant multiple, times the limit as x goes to infinity of x to the n. But now we're in good shape, because there's no extra coefficients, there's no stupid shit in this guy. We already proved, that was this exercise, right? We already proved that the limit as x goes to infinity of x to the n equals infinity. Where, again, by equal I just mean this, again, same nonsense. So I can go through this more carefully after we have the proof, because this step is not yet justified. But once that is justified, then we can run this argument that for any sum of all of these guys with any coefficients, positive, negative, whatever you want, the thing, as long as an, sorry, I should be careful, an, if that's negative, then this goes to minus infinity. That's the only sign that matters, is the leading guy. But if an is positive, the whole argument goes through and the guy goes to infinity. If an is negative, the whole argument goes through and the guy goes to negative infinity, and all of the other terms just die. Good. Is that the question you were asking?
Yes, and indirectly you answered another one of my questions. If there is some point where the foremost term outpaces everything else.
Yeah, that's true. it's always true that a polynomial of degree n dominates every polynomial of lower degree, n minus 1, n minus 2. What do I mean by dominates? So, definition, we say f, I like this term because it sounds kind of kinky, f dominates g, like there's handcuffs and whips involved. F dominates g if the limit, now I can talk about limits at infinity, right? We define this. The limit as x goes to infinity of g divided by f equals 0. What does that mean intuitively? Well, that means as the inputs get bigger, f is growing way faster than g. How do we know that? Because f must be growing way faster than g, because apparently this fraction is going to 0. And if the fraction is going to 0, that means the denominator must be much bigger than the numerator. F is dominating g. So I think we said this once before in the context of I was telling you that, a polynomial is always going to be dominated by the exponential. Limit as x goes to infinity of x over e to the x equals 0. So e to the x just swamps this guy. But now I keep using this result I haven't proven yet, but if you believe the super L'Hopital rule, then this is obvious. You just take the derivative of top and bottom, limit as x goes to infinity of 1 over e to the x, and as e to the x gets larger, 1 over a large number, this guy goes to infinity, so the thing has to go to 0. So if you have super L'Hopital, one other comment, you could probably see that it doesn't matter if there's a power here, right? Because if this were x to the power 100 over e to the x, then just take the derivative 101 times, and then, or 100 times, whatever, so till the top's constant. Take the derivative 100 times, and then it's back down to this guy. So it's 0. So anyway, this will be a proof once we have it written out nicely that e to the x dominates every polynomial, and it's probably pretty obvious that every polynomial with big degree is going to dominate, polynomial with a smaller degree, because he grows faster eventually. Good. Other thoughts about domination?
Hearing that without context is a great.
Should just grab that snippet from the YouTube video and send it to people at random.
Yes.
Good.
A few people that need it.
Yeah, I might be a bit embarrassed, but okay, good. If you're happy with that,
Next.
if you're happy that yes, every polynomial overtakes its lower brethren at some point. All right, so this is the last proof, which we're going to need for some of that, some of the stuff I just said. We actually need this to go for that argument to go through. So what would we like to do? So for that argument, I said one step which I didn't prove, which was this statement. I said the limit as x goes to infinity of 1 over e to the x equals 0. It's kind of obvious because this guy gets bigger and bigger, so if you divide by a bigger and bigger number, you're getting smaller and smaller, so this goes to 0. But this is kind of the dual of the statement that the limit as x goes to infinity of just e to the x, not the inverse, is infinity, right? So you might say, can I just swap these two statements whenever I want? If a function goes to infinity, do I know that 1 over that function goes to 0, right? And indeed, something like that is true, so we should prove it. I don't know if it should be called a proposition or a theorem. I guess it's not a big deal. But, so anyway, suppose f is a function whose domain includes at least 0 to infinity. It's defined on the positive half line. And if either of these two limits exist, so we have to do two proofs, right? We assume that one of these limits exists, so maybe the limit as x goes to infinity of f exists. Then we want to prove that the limit as z goes to 0 of f of 1 over z exists, and they're equal. And if the right side exists, then the left side exists. So this is just making the kind of obvious observation that if, let's see, how should I say this? Yeah, I'll go back to this thing. If f of x equals... Actually, this is a little different than what I said. No, ignore what I said. What I was talking about is limits of quotients of functions. That was totally unrelated. Sorry. I lied. This is about the inputs. It's about the inputs x and 1 over x. So I use a different letter z. Right? So this is saying that if a function approaches some number say L. My pen's not working. Here we go. Function approaches some number L at 0. This is f of x. Then if I plug in 1 over x to define a new function, I define a new function f by plugging in 1 over x. Well, when x gets close to 0, 1 over x is getting close to infinity. So this guy, f of 1 over x, I don't know what he looks like elsewhere, but he better have a horizontal asymptote where he goes to L at infinity. That's this thing. This is different from what I said before. I lied. So anyway, this is just trading 0 for infinity. If you have a limit at 0, define a new function by plugging in 1 over the old variable. When the old variable goes to 0, the new variable goes to infinity. So the new function has a horizontal asymptote whose value is the old guy's limit at 0. Okay, that's the correct statement of what we're proving. Okay, how do we prove it? Well, this is really a fancy way of saying I can take 1 over a number. Okay, so here's the first half of the proof. Suppose the limit as x goes to infinity of f of x exists and it's equal to L. I'm going to prove that the guy on the right exists. To prove the guy on the right exists, we use the old-fashioned definition epsilon delta. There's no infinities on the right side. This is just standard vanilla epsilon delta. So how do I do that proof? Well, as always, let epsilon greater than 0 be given. I need to show that I can make f within distance epsilon of L by approaching z from above. Notice we're doing a one-sided limit. So I need to pick my delta. How do I pick a delta? I'm going to pick delta to be 1 over n, where n is chosen using this limit at infinity. So again, in this part of the proof, we're assuming the limit infinity exists. If the limit at infinity exists, then by the definition of a limit at infinity, for this epsilon, I can find an n, so that whenever x is bigger than that big number n, this f will be within distance epsilon of L. So I'm assuming that this limit exists, pick that n. Then since I have to prove that limit exists, I have to hand you a delta. Well, I grab that n that I just cooked up and define delta is 1 over n. Why does that work? Well, I have to prove that the usual epsilon delta definition works. So if this new variable z is within distance delta of 0 from above, on the right, then by simply taking 1 over, which flips the sign of the inequalities, 1 over z must be bigger than 1 over delta. 1 over delta is simply n. So if 1 over z is bigger than n, then by the assumption that the first limit exists, this means f at 1 over z minus L is within distance, sorry, f of 1 over z is within distance epsilon of L. Man, I'm butchering this. Anyway, this is true because it's just this equation. It's just f of x, where we're using x equals 1 over L. So there's no magic here. It looks like a lot of words, but all we're doing is kind of mapping x going to 1 over x, which is z, and then roughly we have a proof that gives us a big number n, and we're just trading that big number n for a small number delta, and then the rest of the proofs go through. Okay, so that's the forward direction. You assume this limit exists, prove that it's equal to this guy. Let's do the other one. So assume this guy exists, prove that this thing exists. So you can probably guess what that's going to look like. Now, since the limit on the right exists, we're allowed to get a delta, and we have to cook up an n, so we might as well just make n 1 over the delta. How do we work? Okay, so suppose the limit of this f of 1 over z exists, and it's equal to L. I have to do the epsilon delta junk, so hand me an epsilon, give me some epsilon greater than 0. I'm allowed to use that this limit exists, so by definition of the ordinary limit, I can choose a delta greater than 0, so that whenever the input is within, the input z is within distance delta of 0 from above, then the output, f of 1 over z, which is this function, is within distance epsilon of L. So I grab that delta. I know I'm guaranteed that delta exists because we assumed this limit exists. I grab that delta, and then I still have to give you an n, so I say fine, alright, my n is 1 over that delta. You say, why does that work? You have to prove that when x is bigger than that n, the output of f is going to be within distance epsilon of L, and I say, sure, I can prove that. Whenever x is bigger than n, then this means 1 over x is less than 1 over n, and 1 over n is delta. So 1 over x is less than delta. So that means by the definition of this thing, I've just written this in a funny way to remind you. I mean, this is f of x, but I'm writing it as x is 1 over x, because here the variable z is kind of getting mapped in this correspondence to this 1 over x thing. So this is really 1 over z, but we're changing variables so that z is 1 over x, and then 1 over x is giving us the x back. So again, same thing. We just assumed this limit exists, did some change of variables, and then wrote the definition of this limit in these variables, and it gives us the existence of the other limit. So the limit as x goes to infinity of f is L. Okay, good. That finishes the proof. So works either way. You can trade 0 for infinity. It's a very common trick, especially in complex analysis. It's much easier to study behaviors of functions near 0 than behaviors at infinity, because infinity is not really a number. Cool. That's all I got. Thoughts or comments on this?
I do not have any thoughts or comments.
Cool beans. Well, perhaps I should leave you to finish your schoolwork for tomorrow. Remind me, what did you say you were doing tomorrow all day?